welcome grade 12s. Today's lesson is going to look at electrodynamics. It's a really nice section, probably one of the last sections you've done, so it should be fresh in your minds. And remember, electrodynamics is one of those sections, 10 to 15 marks in your physics paper, guaranteed to be in there. It's one of those sections you definitely going to get. The nice thing about it is that it's all the same. The wording changes a little bit and it looks a little different, but it's always the same. So it's a nice easy section, easy marks. What we're going to do is we're going to go through a little bit of what you should know, a summary of the things you should know to start off with, and then we're going to look at some questions. These questions have been taken from past papers, and that'll really show you that they're all the same type of thing, just worded slightly different, okay? So let's just jump straight in, and we're going to look at our summary. So number one, you must be able to explain how a motor and a generator works. This is really important because a motor and a generator are very different. Remember, a motor uses electrical energy, changes it to mechanical, whereas a generator takes mechanical energy and changes it into electrical. Added to that, and this is where they like to try and trick you out, okay, is remember we get AC and DC motors, okay, alternating current, direct current, and we get alternating current and direct current generators. We get both. They'd like to try and trick you with this one. You're going to see with our questions that they're going to ask you the difference between the two. Very important, and it's a very subtle difference which you must understand. You must be able to describe the components of these electrical machines and explain the function of each. So you need to know what they do, what they look like, and what their function is. In particular, they're going to ask you about things like the carbon brushes, which are very important, the armature, which your coil sits on, and your commutator, whether it's a slip ring or a split ring, okay? Next thing you need to be able to do is state what factors affect the speed of a motor or the EMF of a generator. What are the things that we would change, increase, decrease, put together to make the motor go faster, okay, or to make it go slower, or to make it run more smoothly, or the things that will increase the voltage, the EMF of the generator, not the current, okay? Then we need to be able to compare direct current and alternating current, both in words and in diagrams. Particularly in diagrams, you need to be able to see the difference in the graphs. And then with alternating current, we're going to ask you about the graphs for alternating current, and then we're going to ask you to do calculations on the alternating current. The calculations for alternating current is new to the curriculum, so they actually quite like asking that. And that's where we're going to go to by the end of the show. Let's jump right in there and do our first question. What we have here says to us, electrical motors are important components of many electrical appliances. So what you do is you go, okay, I'm looking at electrical motors. So we go, fine, it's a motor, which means there's going to be a current in my coil. I'm not creating the current, and there's going to be a current in the coil. That current, when it interacts with the magnetic field, is going to cause the coil to turn. Okay. AC motors are used in washing machines and vacuum cleaners, and DC motors are used in toys and tools. Hopefully you guys realize that it would make sense to use an AC motor in something like a washing machine, vacuum cleaner, because we plug it straight into our wall. So we plug it straight into an AC supply. In toys and tools and that sort of thing, they use batteries. Batteries are DC supply. Okay, so first thing we put in our head. Now, the first question says to us, what energy conversion takes place in an electric motor? This is one of those guaranteed things, and we go, okay, we thought about it at the beginning, and we went, the electric motor has a current flowing through it, which means we're starting with electrical energy, okay? And that's changing to something. Here we've got to be careful. We talk about mechanical energy. Kinetic energy isn't strictly speaking wrong, but they don't really want it. They actually want, and in this case they want rotational mechanical energy. Now,
kinetic energy is okay, but it's not specific enough. Grade 12s, they're really looking for whether you understand that in a motor, it doesn't just start something moving randomly, it starts it rotating, and that rotation is what we're looking at. Why am I calling it mechanical energy? Because it's still a form of kinetic, okay? It's still a form of that motion that causes, that energy that causes a motion, okay? It's mechanical in nature. Very, very important. Nice, easy question. Our 2 marks are done. Make sure, please, that you get it the right way round. Electrical to mechanical. Then, they say to us, next part of the question, what is the essential difference in the design between DC and AC motors? They're wanting you to be able to bring down to the very, very basic core. What is the difference? The design is in the commutator, okay? It's in the commutator. In a AC motor, we have slip rings. In your DC, we have a split ring. Okay? We have a split ring. In an AC motor, your slip rings turn. You have your 2 rings, and then your 2 rings allow for constant contact, and as the coil moves, it's fun. It'll just keep going in the same direction because of the way the current goes backwards and forwards. In your split ring with a DC motor, you need the split ring so that every half turn, the current changes direction in the motor. Because if it doesn't, what will happen is your coil will actually end up going backwards and forwards. It'll flip-flop the whole time because of the way the current goes through. So you need to have your slip ring and your split ring to make sure it just keeps turning. Very, very important. It is the commutator. Okay, you got that? It's the commutator that changes it. Your commutator has lots of functions, guys. Besides allowing the constant flow of current essentially in the same direction in the coil between the magnets, it also allows for things like, 1, it stops the coils from getting all caught up in each other, because if we don't have that nice solid ring, they turn and then they get split up, they get twisted on each other, which doesn't really help us. And it allows for constant contact with the circuit, which is where we then put the brushes in. Everything else about your DC motor and your AC motor is the same. It's the commutator. We okay with that? I hope so. Then, nice question. List, careful here, 3 ways in which the efficiency of the motor can be improved. I'm not asking for how do I make it turn faster? I'm not looking for that. I'm asking you, how can I make it more efficient? In other words, how can I make it so it turns smoother? How do I make it so that the turning motion makes more sense? It only says 3 ways, grade 12s. What that means is you could write 100 ways, and we will only mark the first 3, because we only wanted 3, okay? So don't write everything you know. Don't go and just write everything you can think of. Think about it carefully. The first 3 are what we're going to mark. Now let's think about the fact that we want this coil to turn. What's actually happening in a motor? We have a magnetic field going from side to side between the magnets. As current goes through the coil, that current creates another magnetic field, okay, and those 2 magnetic fields are interacting. If we can make that interaction stronger, then we can make it be more efficient. We now think about this and go, well, logically, if I want a stronger interaction, then I need stronger magnets. Absolutely. So number 1, stronger magnets. Okay? Please be careful here, grade 12s. Often you mean stronger magnets, but you write bigger. A bigger magnet isn't necessarily a stronger magnet. It's just bigger. there's just more of it, okay? We want a stronger magnet. We want a stronger magnetic field. Be careful there. Number 2. So the magnets have something to do with the magnetic field, but so does the current. Because if we remember back, we go, well, a moving current in a conductor creates a magnetic field. The magnetic field size is determined by the current. So if we want a bigger magnetic field in the coil, we need a stronger, actually probably here would be better, a bigger current. Okay? Those two, fairly straightforward, nothing difficult. The third one is now we've got to think about this and go, okay, we have a wire in a magnet, and we want to increase the efficiency. We're not going to increase the current because for whatever reason we can't, but every coil that's in my magnet adds to the magnetic field. Therefore, if I add more coils, I have more, essentially more current going through it once. So all the coils are on top of each other, they're next to each other, which means all the magnetic fields increase in self, they reinforce each other. Okay, that means the third thing we can do is increase, okay, the number of turns on the coil, okay? Ooh, maybe I should spell stronger right for you. Stronger magnets, bigger current, increase the number of turns on the coil. Guys, please be careful here, because from a practical point of view, things like making sure the armature is properly oiled, making sure the brushes have nice contact, all of those sort of things, obviously they play a role in the efficiency and they play a role in how smooth it runs. But I'm not concerned about those things right now. What we're looking for in this question is, do you understand that there's a relationship between electric currents and magnetic fields? That's what we want. That's the essence, okay? This was a nice long question, so let's look at the next one.
Now consider the diagram below. The conventional current flows in the direction indicated by the arrows, and they very nicely put it on there for us. And they ask us in which direction, clockwise or anti-clockwise, as seen from position A, will the coiled armature rotate if the switch is closed? Now, grade 12s, there's a couple of important things here. First of all, the question says that it's clockwise or anti-clockwise. This means you can't write up, down, left, right, north, south, anything like that, because they don't want that, and it doesn't make sense. Now, position A is on the right-hand side of my diagram. It's over here. Conventional current, remember, goes from positive through my coil through to the negative. Very important. So by clockwise or anti-clockwise, let's just remind ourselves which one is which, okay? Clockwise means it goes in the same direction if you look at a clock, which is actually round, well, actually you look in the TV, so it's probably the wrong way around, but for me, it's going this way around, so it's to the right. So I would say if it's going up and then across, that's clockwise, so I'm going to put CW. If it's going the other way around, which we want sometimes to turn time back, that's anti-clockwise. That's just for me to remember. That means when I look at my diagram, I now have to decide, is this coil going to go up or down? If this side of the coil, position A, is going up, then it's going anti-clockwise. If it's going down, then it's going clockwise. Okay? How do we do this? Well, we use our right-hand rule. You might have been taught it like this. You may have also been taught a left-hand rule. It doesn't really matter, grade 12s. I'm going to stick to this right-hand rule because this is the one that is actually in the curriculum. The other two, they work. You're free to use them if you fully understand them, so it doesn't really matter, but just keep with me, okay? Make sure you know your left from your right. That's very important. I know I get confused sometimes, but this is my right hand. Now, on your right hand, your fingers, which lots of them, must always point in the direction of the magnetic field. So the first thing we have to decide is, which way does the magnetic field go? Nice way to remember it is magnetic fields always point to south, okay? Right hand must point south, okay? Points to the right on my diagram as I'm looking at it. Then my thumb has to point in the direction of the conventional current. So if I'm looking at my coil at position A, when I'm looking at it, it's sort of going into the page. So I would put my coil going, my thumb's going this way, okay? North to south, pointing out. Now the palm of my hand, okay, the palm of my hand is actually pointing down. If I could see this as a three-dimensional thing, it's very difficult when it's flat. What is actually happening is it's going from north to south, my coil is going away from me, and my palm's pointing down. That means the palm is showing the direction the coil moves. So, if I draw this in, my coil is moving down. At position A, the coil's moving down. The other side of the coil is attached to position A. It's one thing, so it can't go down as well. And let's just double check to be on the safe side. North to south for my magnetic field, okay? The current is going in the opposite direction, and now my palm's pointing up, okay? That means the other side points up. Now we consider this and we go, okay, look at what I said. If it's going up and then down, that means my coil on the armature is turning clockwise, okay? Clockwise. So we would need to write it down as that. Like I said, don't go in right, left, right, up, down, because I know it is so tempting. It's going down. But they didn't want that. They said clockwise. So we write that in and we say, well, it's going clockwise. Okay, it's only worth 1 mark, but it's a lot of work for that 1 mark. Okay? But grade 12s, we're not quite finished. We now need to look at the next question, which is 1.4.2.
It says now, why does the armature continue moving in the same direction once it has reached the vertical position? And you guys are going, well, that's a bit stupid. Why wouldn't it? When it reaches vertical, no force, okay? There is absolutely no force on the wire anymore, none whatsoever, 0. But it does keep moving because as it turns, the coil gains momentum, and that momentum tips it just enough for it to experience a force again. Remember, 1 degree either way of that vertical position, it experiences a force, it's going to keep rotating. And eventually, remember, these spin very, very quickly. We're not talking about a slow little spin, you know, it's like a hamster on a hamster wheel. All right, fast, 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 fast. And you guys have all played with toys that have motors in them when they spin very, very fast. Fans are very good examples of where we use electric motors. Okay, it's a very good application because the fan turns and you know that you can change the speed of the fan. Okay, it keeps turning because of its momentum. All right, you guys got that? Are we okay with that one? It's a nice section. What we're going to do now is we're going to take a short break. When we come back, I've got a couple more questions for us to do, also from past papers. So take a break, get a drink. We'll see you in a couple of minutes. Welcome back, grade 12s. I hope you're ready for the next section. We're going to carry on with our electrodynamics, looking at motors and generators. And now the last question we looked at was a motor. What we now need to look at is what happens with a generator. So we have a question. Let's just jump right in there. The simplified sketch below shows the principle of operation of the alternating current generator. AC generator, there's a whole bunch of stuff here. We have the direction, oh, maybe I should put pen there, hey. The direction here is showing you the direction of the magnetic field. This is my north pole, this is my south pole, brilliant. And then there's a whole bunch of things that are labeled, okay? So we go, before we even look at the question, grade 12s, this is really what you should do. Don't look at the question, look at this and go, okay, what do I know? Well, if I look at part A, the arrow's got a little moved, but part A is actually at this, pointing to the slip rings. Now, I know it's slip rings because it's a generator and it's an AC generator, okay. Part B is to the carbon brushes, okay. Part Q is probably the armature. It's a little difficult to see, but it's probably the armature. Okay, part Q is referring to the coil, and X and Y together will be the output. Okay, that will go to the external circuits, and now we can't say which one's positive and which one's negative because it's an alternating current, which means it keeps changing direction. Okay, so we go, cool, that's brilliant. Let's see what the first question says to us. Look at that. Name the parts labeled A and B respectively. We've just done that. A is the slip rings, B is the carbon brushes. Please, grade 12s, when you write this down, you need to do it like this, where you go A, slip rings. B, carbon brushes. Please don't just go slip rings and carbon brushes. We really need to know, you know, which one's which. Okay, very, very, very important. Not so bad. Part 2.2 actually says, in which direction does segment PQ of the coil have to rotate in order to cause the current direction as shown in the diagram? So really, when we come back and we go, okay, P and Q weren't showing the armature and the coil, so let's just take that out. That's fine. So we go, okay, not a problem. But they are saying to me, now we're going to use our right-hand rule again. I love this rule. The current is going in that direction. Where must PQ go? Anti-clockwise? Clockwise. In other words, they're asking you, must PQ go upwards clockwise, or must it go down anti-clockwise in order to get the current in that direction? Right hand again, same thing, right hand. Fingers point in the direction of the magnetic field. Okay. Your palm actually points in the direction of the current in this case. Okay. And your thumb points in the direction of the force, of the direction of the conductor, okay? Because in a generator, normally you will be given the direction it's turning in, and then we use the palm to find the unknown. So here we go, all right, north to south, so it's going north to south. The current is going into the page, so my thumb is now going up, okay? Thumb's going up. That means it's got to go clockwise. Okay, next. Write down 2 changes. 2, like I said to you before, don't go write down 400. 2 changes that can be brought about to improve the output, increase the EMF. That's what they're asking. All right. Think about what we did in the last question to increase the efficiency. We increased the number of turns in the coil. Surely that's going to make a difference? Of course it is. The more coils we have, the more wire we have in the magnet, the greater the EMF. You know that as well from Faraday's law. Okay, remember Faraday's law says to us that the EMF will be in changing phi over changing time, n being the number of turns. Okay, number of turns. So the first thing we're going to do is we're going to increase number of turns. Okay, brilliant. Number 2, the other thing we could do with the motor was we could increase the magnetic field strength. So let's do that. Use stronger magnets. Okay? We cannot say increase the current because that's what we want to do. All right? By increasing the current in a motor, we made the speed better, more efficient. A generator is like the opposite of a motor. So in a generator, instead of increasing the current, we're going to increase the speed of rotation. Increase the speed of rotation. Turn it faster. Any of that. There's a fourth thing we can do, which is quite an unusual way of doing it, but it's perfectly normal. You could use a horseshoe magnet. So here, instead of using 2 separate magnets side by side like that, you use one of those horseshoe magnets. Let's just go to the bottom over here. A horseshoe magnet, remember, is our round magnets with and they would do that. This would be, say, north, this would be south. What a horseshoe magnet does, grade 12s, is it concentrates the magnetic field, makes it a lot stronger, okay, which we like and that's what we need. But I wouldn't increase the magnetic field strength and then say use a horseshoe magnet in the same as 2 of the same reasons. It's really the same thing, just writing it in different ways. Okay, then, next question. What changes? Brilliant, because this is very similar to the last one. What changes must be made to the AC generator to make it function as a DC motor? Okay, first of all, important things. 1, change AC to DC, generator to motor. First of all, how do we change between AC and DC in both a generator and a motor? We go from a slip ring to a split ring. All right? So we say first we need to change from a slip ring commutator to a split ring commutator. First thing, if it was just changing an AC generator to a DC generator, question answered. But they wanted us to change it to a motor, which means you now need to add a battery. We need to add an energy source. So instead of having a source that turns the coil, we take that away and we put a battery into it, okay? Because we want to change electrical energy into rotational mechanical energy instead of taking rotational mechanical energy and turning it into electrical. Okay, we okay with that? It's a bit of a nasty question because sometimes you don't always see the fact that I'm wanting you to change from a generator to a motor. Okay? Let's head on into our next question. You're doing great. Hang in there. Okay, now we've got another question. This is actually a really nice one. It says to us, diesel electric trains make use of electric motors as well as generators, so they use both. The table compares a motor and a generator in terms of the type of energy conversion and the underlying principle on which each operates. So, now I've got a very small space, but we've spoken about this already today. A motor goes from mechanical, okay, no, sorry, I'm lying to you again. Electrical was the first question we did. Electrical, oh, I'm going to run out of space, to mechanical. Okay, and a generator goes from mechanical, let's try to write it so you can actually read it, to electrical. Now, in a tertiary exam, you would write this out. Principle of operation. Wow. This is where the wheels fall off a little bit. So now you go, ooh, I don't know. We're busy with electrodynamics. In a motor, it's the easiest one to remember because the principle of operation, excuse me. Oh, look at that. It's the motor effect. I can remember that. The generator's a little harder, okay? The generator comes from the principle of electromagnetic induction. Electromagnetic induction. Not Faraday's law. Faraday's law helps us find values and calculations from electromagnetic induction, but it's not Faraday's law. Okay? Next one. The simplified diagram below represents an electric motor. Give a reason why the section of coil labeled BC in the above diagram does not experience a magnetic force whilst the coil is in the position as shown. This is actually the simplest reason because this is what the direction that your magnetic field's going in, okay? Goes this way. Looking at this nice mathematical principle, BC is parallel to the magnetic field. Simple as that. BC is lying parallel to the magnetic field. Now, what is actually happening here, grade 12s, is the magnetic field that's created around BC, because there is a current going through it, goes like this, okay? Goes in circles around this way. The magnetic field, so it's going this way around. The magnetic field that it's in goes in this direction. Now that means that these two magnetic fields are perpendicular to each other. And the one thing about magnetic fields is when they are perpendicular to each other, they cannot interfere. They will not interfere with each other. They have to be at an angle or parallel. They cannot be at right angles. So because the coil is parallel to the magnetic field, it experiences no force whatsoever. Okay? No force whatsoever. Second thing, and that's an important one, but the second thing is, look at what they did. They left the switch open. There's no current. Okay? In reality, that's a far more important reason than it being parallel. It wouldn't actually matter where it is in the circuit. It could be vertical, it could be at an angle, it doesn't matter. The switch is open. Open switch, no current, no force. Simple as that. Okay, now, we do have one more part to this question, but it's a calculation-based question on alternating currents. So what we're going to do, grade 12s, is we're going to go for a quick break. I want you to make sure you come back with your calculator. We're going to go for a quick break, and then we're going to get stuck into the calculations for this section, which I know you do not like, but you are going to get. So we'll see you in a couple of minutes. Welcome back, grade 12s. I hope you had a nice little break. Remember, I said to you before the break that you need your calculators. We're going to get stuck into the calculation part of it. One of those things I know you're going to get. Okay, let's get straight into it. Same question that we were busy with, but another part is actually separate to everything else that was on there. Says to you that we have two graphs of current and potential difference outputs of an AC generator as shown below. Now what we have here is we have a current graph, so this is current. We have a potential difference, that's V over time. What we note about our AC graphs is that they are both sine graphs. That makes it really, really nice. What these graphs are showing me is they're showing me the maximum current and the maximum voltage. Positive, negative, both sides, okay? So what they're saying is we can say, okay, Imax is 21 and Vmax is 311. Now we go, okay, they want average power. Average power. There are so many ways you can do this. But on your information sheet, because this is probably the one you're going to remember, your information sheet says to you that average power is equal to VRMS times IRMS. So we go, okay, I don't have VRMS and I don't have IRMS, but I can work them out, because also on your information sheet, let's start with VRMS. VRMS is equal to Vmax divided by square root 2. What's nice about this grade 12s is that you don't need to show where this equation comes from. Right back in the beginning of the curriculum, they said you would have to, but you know what, you don't have to. It's statistical average. It's got to do with trig and all sorts of things. We're not going to worry about it. Just make sure you can use it. The maximum voltage, well, we got from here is 311. So we go, all right, so we've got 311 divided by square root 2. We go on to our calculators, 311 divided by square root 2, and we get 219,91. Guys, please use the rounded off number. 219,91. Okay? Let's do IRMS. Okay, I'm just going to put a line through this because I want you to see the way we lay it out. That was just for me. So IRMS is going to be, if VRMS was Vmax over square root 2, IRMS is the same, but with I. So it's going to be I maximum divided by square root 2, and we go, ooh, let's see what it was. It was 21. 21 divided by square root 2. Let's quickly work it out. And, ooh, please don't leave it like that. Come now. 14,85. Okay. All right. I have VRMS, I have IRMS. Let's do this. P average is VRMS times IRMS. VRMS was 219,91. This is 14,85. And okay, so 219.91 times 14,85, 3,265,66. Brilliant. 3,265,66 watts. Brilliant. I want to show you something else. Nice way. Yeah, you know, we sort of go, lots of calculations. It's okay. We can manage that. I want to show you something else, though. We could have very easily have done this. Maximum power is maximum voltage times maximum current. My maximum voltage was 311. My maximum voltage was 21. And I get 6,531 watts. Now, some of you are looking at me and going, hang on, wait, Tracy, they didn't want maximum, they wanted average. The nice thing about power is never negative. So the power of your AC generator goes from 0 to its max, to 0 to its max, to 0. So the average is equal to the maximum divided by 2. Okay, no, don't do that. Let's do it underneath each other. So it's 6,531 divided by 2, and we get 3,265,5 watts. Now, I'm hoping those of you that are really paying attention are busy going, hang on, wait, Tracy. No, we have a problem. The average you just worked out above is 3,265,66. That is not the same answer. No, it's not. But this one, the reason why we have a difference is because of the rounding. Okay? It is because of the way we round off. Because we round off at every step, because we rounded off when we found RMS and VRMS, we get a different answer. If you stored both of those into your calculator, okay, you would get the same answer. Or if you did it in the sum. So in other words, if we did this, if we went, okay, let's calculate, so we got 21 divided by square root 2 times, oh no, there we go. Oh, there we go, sorry. Oh, it's because I put the bracket there, sorry, okay. I don't actually know how to get rid of the bracket, there we go. Square, okay, times 311 divided by square root 2. Look at that. Now I didn't, that keeps the same answer in the whole time. And look at that, I get exactly the same answer as I got when I divided the maximum in half. It doesn't matter, okay? It is, excuse me, it is the rounding. Leave it as it is. We're quite happy with that, okay? Hopefully you guys are happy with that. I know it sometimes freaks you guys out, especially those of you who are much better at maths. Leave it, it's the rounding off. Please do not then keep all your decimal places for these ones, because you're just going to get yourself into trouble. Round it off to 2 decimal places. Okay, last few minutes. Let's get into the last question. Here we go. The waveform on the following page is a graphical representation of the variation of voltage versus time for an alternating current. Now it's on the same page, so it doesn't matter. Here we go. All right, let's see what they've given us. They've got minus 325 maximum, that's time. There we have 0. Oh, brilliant. Not a calculation. Darn. Explain the advantage of using alternating current at power stations. 2 marks. I need 2 things. This one's really important. When we transport our current over long distances, if it's transported at a very high current, high ampage, lots of heat gets generated, we lose a lot of power. If we can transport it at a very low current, we get a lot less heat, lot less power loss, which means what we need to do is have a very high voltage with a very small current. And if we remember from grade 11, okay, when we looked at transformers, if we go VI in the primary is equal to VI in the secondary part of a transformer, if I make the current really small, I can make the voltage really big. So we can increase the voltage. We can only do that with an alternating current. An alternating current, we can transform an alternating current. We can increase the voltage in order to decrease the current to lose less power in the transportation of it. You cannot transform a DC current, a direct current. If you want to try transform a DC current, you have to switch it on and off. That would just be a really boring job for someone. So for an alternating current, it's really simple, goes through the transformers. We can transmit it over our power lines at extremely high voltages, tens of thousands of volts. Then step it down for industry, which depends on where it is, gets between about 40,000 to 500 volts, to our homes, which is 220, 240 volts, okay? Makes it a lot easier. So that's the advantage. We can transform it in order to transmit our electricity at high voltages, low current, okay? Brilliant. Time for one last little question. Calculate, same thing, the average power dissipated by this generator if the RMS current produced is 13 amps. All right, let's see what we got. Vmax was 325 volts, and they've said to us, yay, we like it when they do this, IRMS is 13 amps. We completely have the option here, grade 12s, to do what I did in the last question, find maximum power, divide by 2, which then means I would need to take the RMS, find maximum I. Okay, so now we've got one equation, finding maximum I, then we're finding maximum power, then we're finding average. 3 equations only worth 5 marks. Nah, let's not do that. What I can do, though, is take my maximum voltage and find my VRMS. Easy, because then I only have to find VRMS and then I can find average power. So let's do that. So VRMS is equal to maximum divided by 320. Oh, no, what am I doing? Vmax divided by square root 2. So that's 325 divided by square root 2. So let's see what we get. If my calculator, there we go, 325 divided by square root 2. 229,81. Okay, don't forget the right, make sure your rounding's right. Let's see, 229, there we go, comma 81. Okay, brilliant. We knew the RMS current was through 13. So average equals VRMS times IRMS. 229,81 times 13. Now I know at this point what a lot of you want to do is go, oh, the answer's in there already, let's use it. Please don't, because it's going to mess up the decimals and then it becomes a nightmare to mark. So 229,81 times 13, 2987,53. Okay, 2987,53 watts. Done. That's your average power. Now, of course, you could have done it the other way around. It's really up to you. It's only worth 5 marks, though, okay? Please, please, please don't forget units. Okay, grade 12s, we have covered a lot of work today. You are going to get some calculations, like the RMS, the alternating current, all of that sort of thing, but you are going to get those questions, and I'm hoping you realize they're all the same sort of thing as what is the function, what are the parts of the AC motor and the DC generator and the DC motor, what do they do, how does it work, what is its function, what is the energy conversion, all of that sort of stuff, grade 12s, okay? So go make sure you know your theory. You are going to get something, okay? I promise you, you are going to get something, either a motor or a generator or both. They can give you a combination, like you saw in that question where they asked you how you convert from one to the other. Make sure you know your theory. That's really, really, really important. All right? I hope you find this useful, grade 12s. Good luck for your finals. And that's me, and I'll see you again next time.